Hello everyone, welcome back to the final lecture of this course on measurement and instrumentation, and today is also the 5th lecture of our 12th week, and in the course this is the 60th lecture. Today we will summarize overall course of whatever we have discussed over the last 12 weeks. We started with this course with the objective to understand the fundamental of measurement system. The second objective of our course was to learn principles of analog and digital instruments. Third objective of this course was to explore different transducers for physical quantity measurements, like transducers for temperature measurement, transducers for strain measurement, and so on. And then final objective of this course was to study signal conditioning and data acquisition techniques. These objectives were dispersed in this course, and we have divided the complete course in 5 different modules, which was spread over 12 different weeks. In the first week, we have discussed about fundamental of measurement systems. Next week, 2nd to week 6th was totally devoted to analog meters, which constitute the major part of our course. Then week 7 and 8 was dedicated to transducers, and in week 9 and 10 we discussed about different signal conditioning techniques. Okay. In the final weeks, week 11 and week 12, we have seen data acquisition system, including the signal analyzers, as well as finally how the data that we have acquired in the first stage or by the transducers are displayed on the screen, or more convenient way to store these data. So we started with data acquisition or data acquiring to display in this course. So this is what we have seen over from week 1 to week 12. Let us see in little brief that what we have seen in each of these individual weeks. Okay. In the first week, we have discussed about fundamental of measurement system. We have defined the measurement system, and we have seen what type of measurement systems exist. We have classified the measurement systems in different ways. We have done classification like primary and secondary instruments, active and passive instruments based on the power supplies to these instruments. Then we have also seen deflection type and null type instruments, analog and digital instruments, and smart and non-smart instruments, including the IoT based devices or IoT enabled systems. Okay. Then we have emphasized on characteristic of measurement system, because characteristic of measurement system is something which we require till our 5th module. So we have seen the static and dynamic characteristic of these instruments in detail. Okay. We have also talked about noise and source of noise, including the generated, conducted and radiated noise. We have seen their differences and their sources. Then along with noise, we also discussed the errors in the measurement system, and overall we have seen that there are different type of errors that can occur. Some are due to the person who is taking the data, and some of them are due to the instruments limitations. Okay. We have seen gross, systematic and random errors in detail. Okay. Then we talked about different parts of a measurement system, including its electrical, mechanical, thermal, all these parts, because all these analog meters that we have seen in our next module were constituting the electromechanical system. So it was essential to understand the electric part as well as the mechanical part. Okay. Measurements is based on comparison with the standard and require proper instruments for that kind of standardization, and we have seen that under calibration. Okay. A measurement system including sensing, conversion, manipulation, transmission and presentation of whatever measurement has been done is essential, and that is what the objective of this first week was, to get acquainted with all these systems which we have studied from week 2 to week 12 in detail. Okay. Then desired characteristics like accuracy, precision, sensitivity, resolution, reproducibility, usually we want on the higher side, while there are certain undesirable characteristics like drift, threshold, dead zone, dead time, we want it to be at the lower side. So we have seen that through this static and dynamic characteristic, from the user point of view, we have understood that what are these characteristics and how to minimize or maximize some of them. Okay. Then in the second week, where we actually started our analog meters, we just got introduced to the analog meters, and then we have seen different effects used in analog meters like magnetic effect, electrostatic effect, thermal effect, and so on. Okay, and we have studied this along with these effect, different devices, different meters based on these principles. Okay, then operating forces in electromechanical indicating instrument was essential to understand, and we have seen along with operating forces, operating torques, because they are interrelated. We have also seen that because we have mostly used equations in terms of torque. Okay. Then we have classified these analog meters in the second week. We have seen that these analog meters can be classified based on quantity that it measures, based on effect it uses, based on methods used for comparing the measured value. Like we have seen based on quantity, we have seen number of devices like ammeter, voltmeter, wattmeter, galvanometer, ohm meter, and so on. Based on the effect used, we have seen it. There were three different analog meters like indicating instruments, recording instruments, and integrating instruments, and based on the method used for comparing these methods, we have seen that we have a direct measuring instrument and we have comparison kind of instrument, and then we have categorized them under these heads. Okay, we have also seen that based on principle of operation, we have moving coil, moving iron, electrodynamic type, induction type, electrostatic type, thermal type, those kind of devices we have seen in detail. Okay, and then based on the construction and movement, we have again moving coil, moving iron, electrodynamic, induction, different kind of instruments we have seen. I mean, their constructions were totally different, although the principle remain maybe more or less similar. Like we have seen that some of these devices like moving coil, moving iron were based on magnetic effect. Similarly, we have seen other devices also. So that's how we have distinguished among themselves, so that it becomes very convenient to understand it when we studied these devices later on in different weeks. Okay. Based on the nature of signals, we have classified these analog instrument as DC, AC, as well as we have also seen some AC, DC or universal instruments also. Okay. Based on the damping method also, we have classified them as air friction damping, fluid friction damping, eddy current damping, and there were some devices where there were no damping also. We have seen their advantages and their disadvantages, and also we have seen that in some places we cannot totally use eddy current damping, right? So particularly those systems which require certain kind of coiling. Okay, but those places we only can use air friction damping or say fluid friction damping. So these classifications helped us in understanding the analog meters that were discussed over week 3 to week 6. Okay. In week 3, we have seen operating forces as well as their torques in electromechanical indicating instrument, the construction of electromechanical indicating instrument, and then I introduce you to voltmeters and ammeters to measure voltage and currents respectively. Of course, the instruments that we have seen can be converted to voltmeter or ammeter depending on how you connect the resistance in series or parallel and so on. Okay. Then we have seen three different type of torques which you require in operation of any analog meters. So these three type of torques for satisfactory operation of any indicating instrument were deflecting torque, controlling torque, and damping torque, and we have seen their utilization in the measurement of any value like say for current or voltage. Okay. In the week 4, we continued our discussion on analog meters, and we have seen permanent magnet moving coil PMMC instrument in detail. We have seen its construction, okay, which were made up of, like we have seen moving coil, a permanent magnet, then control by spring, then damping, a pointer and scale. I mean, we have seen in brief what is the construction of a PMMC tool, and based on it we have discussed other instruments as well. Like we have seen how say moving iron equipment is different from PMMC, what is happening there, what is different as compared to a PMMC instrument. Okay. Then we have seen their applications. We have seen that how PMMC instrument can be used as a voltmeter, how it can be used as a ammeter, and so on. Okay. In fact, we have seen that all these instruments including the PMMC, okay, how they can be used for measurement of current, like how they can operate in a ammeter mode, how it can operate in voltmeter mode, how it can operate in wattmeter mode, and so on. Of course, all the devices cannot be used for all these modes. Okay, like we have seen for PMMC, moving iron, electrodynamometer, induction, electrostatic type, thermal effect, thermal type, we have seen for all, right. For the PMMC instrument, we have, or in general for all other instruments also, what we have done is we have seen its construction, okay, and then we define its, or we derived the torque equation. For example, for PMMC, we derived this torque equation as N into B into A into I, okay, and which carries their respective meaning, okay. Then we also calculate the deflecting torque and controlling torque. Controlling torque was directly governed by the spring constant, okay, and this deflecting torque and controlling torque were equated at steady state position to get the deflection value. For example, in PMMC, we have got deflection something like this, right, a constant into the current, or you can say that the deflection was directly proportional to the quantity which we were measuring, and based on this the scale of the instrument was also designed. Like here the deflection is directly proportional to I. For some of the instrument we have seen it is directly proportional to I square, right. So based on this, the scale was linear or non-linear, the deflection was only one-sided or it was both-sided. I mean, whenever I say one-sided and both-sided, I mean to say from zero scale. So for one where I have theta is directly proportional to I, the movement was in both the direction across this zero value, while for some of them where theta was directly proportional to I square, the movement was only in one direction, say it was 0, so movement was only say positive, right. It has their own reason we have discussed in this course, okay. For PMMC instrument, we have seen this current was, or say deflection was directly proportional to I, okay. So as this is directly proportional to I, the scale was linear. Similarly, we have seen for some instrument it was non-linear, okay. So PMMC instrument work on magnetic effect and measure the average DC value and have uniform scale. They have high sensitivity, require very small current, and minimal loading effect on the measured current is possible because of this PMMC instrument, okay. In the moving iron instrument, we have seen its construction in detail, okay. Then we calculated its deflection as 1 by 2 I square by k into dl by d theta, and the deflection was proportional to square of the RMS value of the operating current, and the deflection torque is therefore unidirectional or act in the same direction whatever may be the polarity of the current, okay. And we found that moving iron instrument can also be used for the AC measurement, okay. Electrodynamometer type of instrument we have discussed in detail. So we have derived its torque equation using current flowing through two different coils, and using the, we first introduced this mutual inductance concept in this kind of instrument, okay. And we found that the deflection was directly proportional to this dm by d theta, and it is also proportional to the two different currents I1 and I2. One was in the fixed coil and another was in the moving coil, okay. And this was the first time we have got this cos phi term in the equation, okay. For sinusoidal alternating current, the deflecting torque and the deflection are determined by the product of RMS value of the coil current and cosine of the phase angle between them. So we found it like this. We also found that when it is DC, it is just I1 into I2, or if it is same current flowing in the fixed coil as well as in the moving coil, the current was simply I square, okay. So the electrodynamometer instrument having this two coil, fixed coil and moving coil, can be converted into simple ammeter or voltmeter depending on how you construct them or how you connect different resistances in the circuit, okay. We have also seen a different source of errors in this electrodynamometer kind of system using, that was coming from a frequency, eddy current, external magnetic field, and any temperature changes, okay. We have seen advantages and disadvantages of electrodynamometer over other systems that we have seen, okay. We have seen that this electrodynamometer can be used for both AC and DC measurement. They have high accuracy, no permanent magnets are required, and simply the current flowing through this coil can act as an electromagnet, okay. Same calibration is needed for AC and DC, and that's why we also called it a transfer instrument, okay. There were different disadvantages also of using electrodynamometer, particularly they were affected by the stray magnetic field. They have costly construction, and errors due to temperature variations can also happen, okay. It also suffer from poor damping, okay. In the week 5, we discussed about hot wire instruments, and we also talked about other variety of instruments, that is thermocouple based instruments. Okay. We also talked about induction, electrostatic and rectifier kind of instrument subsequently. Okay. We classified first the electrothermic instrument, and there we found that there are different kind of electrothermic instruments, and out of that we discussed hot wire and thermocouple instruments in detail, including its constructions. Okay. We have found that this is a kind of a hot wire instrument looks like. Okay, there is a thread, there is hot wire, and which is connected through this phosphor bronze wire, and there any movement in this thread defines this pointer movement, and we found that this kind of instrument is actually not dependent on any kind of frequency, therefore they can be used for high frequency AC measurement. Okay, in fact they can be extended to for the RF measurement. Okay, they can be used for calibration laboratories, special industrial measurements can be done with this kind of instrument because of this independency from the frequency components, and they can be used simply as a thermal converters. Okay, we also talked about thermocouple instruments, and we have found that this kind of instrument is again based on Seebeck effect, and we have found that how we can use these temperature differences to measure certain kind of voltages. Okay, their applications are again unique in chemical and process industries, in aerospace and automotive, in industrial application, and so on. Okay. In week 6, we focused on measurement of specific quantities like resistance, power and energy, and here we talked about different ways to measure resistance. But before we actually jumped into measurement of resistances, we classified the resistance ranges in different regime. Okay, we discussed that the resistances of the order of 1 ohm and under, we called them low resistances, while the resistance range from 1 ohm to around 100 kilo ohm or say 0.1 mega ohm, we called it medium resistance, and anything above 100 kilo ohm or 0.1 mega ohm we called it high resistances, and we have utilized different techniques for measurement of these. Okay, like we started with measurement of medium resistance, and we have seen that there are different methods, out of which this ammeter voltmeter method was very popular. Okay, but we also discussed that substitution method was also there, and Wheatstone bridge method is also there for measurement of medium resistance, and directly of course you can use ohm meter, but Wheatstone bridge method was the basis for the low resistance measurement. In the medium resistance measurement, we have found that the lead effect is prominent, particularly when you try to measure very low resistances like of the order of 1 ohm or so. Okay, so we have studied that these lead effect can be as high as 20%, 30% for the resistances which has say resistance value of the order of lead resistance. Say for example, if the resistance under measurement is say 0.005 ohm, and if the lead resistance is also of the order of same, say it is 0.00 ohm. Okay, the effect of lead resistance in the measurement is very high. Okay, as compared to the medium resistance that we have just studied. Say if it is certain kilo ohm, say 50 kilo ohm, in that case maybe you can ignore this lead resistance, but when you have resistance under measurement of this order, okay, lead resistance was very critical, and we have seen that based on Wheatstone bridge we have defined another bridge which is known as Kelvin's double bridge method. Okay, and we have used certain resistance or ratio of resistance in such a way that it has totally eliminated any utilization of or any resistance effect of the lead. Okay, so it was kind of providing us a very high accuracy and avoided any lead effect. Okay, then we saw high resistance measurement, and we have seen that there are different methods, out of which we discussed two of the methodologies, which is direct deflection method and loss of charge method. We have defined one guard circuit in this measurement. Okay, similarly, we have seen measurement of power by wattmeter. We have seen that while measuring power of a DC circuit, this voltmeter, ammeter arrangements are fine, but since cos phi is missing in all this arrangement, we have seen that specific measurement tools has to be developed, and which can take care of this power factor as well. Okay, so we have measured this power and energy using the specific induction kind of instruments. Okay. Then we discussed about the measurement of physical quantities like temperature and pressure, and in that we have taken in our 7th and 8th weeks. Okay. In the 7th week, we started our discussion on transducers, and before we actually jump into development of transducers or their working principle, we first clarified the difference between a sensor and a transducer. We have called a sensor which can convert one form of non-electrical energy to certain form of electrical energy, while transducers was tool which can convert any form of energy to any form of energy. And we have given one example of loudspeaker, which is a prominent transducers. Okay. Then another term that came into our mind was actuator. Okay, so we have seen a difference between sensors, transducer and actuator, and in fact we called that actuator as a opposite of a sensor. Okay, so sensor was something which was producing an electrical data signal from a useful energy, while the actuator was something which was providing the certain interesting useful energy from electrical data, and we have seen certain examples like a motor or so. Okay, we have seen different classification of the transducers. We have classified them under different heads, like on the basis of transduction form used, as primary and secondary transducers, as passive and active transducers, and so on. And then we have seen different characteristic of transducer, like input characteristic, transfer characteristic, and output characteristic, which is of certain use of the end user. I mean, end user will choose its transducer based on the input, output, and the transfer characteristic of these transducers. Okay, we have also discussed about different errors in the transducer, including the scale error, dynamic error, error on account of noise, and so on. Okay, the first transducer that we have seen in this course was a strain gauge. Okay, so we have seen that if a metal conductor is stretched or compressed, its resistance changes on account of the fact that both length and diameter of the conductor changes, and also there is a change in the value of resistivity of the conductor when it is strained, and this property we called the piezoresistive effect. Okay, we have seen different kinds of strain gauges, like unbonded metal strain gauge, bonded strain gauges, unbonded metal wire strain gauge, semiconductor strain gauges, then vacuum deposited thin film metal strain gauge, and we have studied some of them, particularly the semiconductor strain gauge, which was completely made up of silicon, means that the piezo resistance was also defined by the silicon, as well as the diaphragm was also defined by the silicon. We have seen its construction and its utilization. Okay, we have also talked about gauge factor in detail, like we have seen that for metal foil the gauge factor is low, like 2 to 5. For thin film metals also it is 2 to 5, but for thick film resistors it is around 100, and for semiconductor strain gauge it was between 50 to 200. Then we have seen that how P-type silicon, N-type silicon, P-type germanium, N-type germanium, how they differ in their gauge factor, and how these values vary from a single crystal silicon and a polycrystal silicon. Okay. Temperature sensors was the another topic which we have seen it with great interest. We have divided temperature sensors in two types: contact temperature sensors and non-contact temperature sensor. In the contact type sensors, we have discussed the thermocouples, RTDs and thermistors in detail. We have seen that the RTDs are something very essential for high temperature measurement, and tungsten RTDs are even used for anything above 600 degrees Celsius. Okay, all RTDs have positive temperature coefficient because they are all based on metallic wires, and several type of them are available from different manufacturers. Okay. Then KTY sensor was another device which we have seen, which was a kind of a P-type or positive temperature coefficient sensor in silicon, which was very specific. Mostly we have seen that NTC devices are there, but for positive temperature coefficient we have seen a specific KTY sensor. Okay, and we have studied its characteristic and which temperature range it can acquire. Okay. In the week 8 of the transducer, we continued our discussion on thermistors, thermocouples, piezoelectric transducer, capacitance and inductance transducers. Like thermistors we have seen in detail that what is a thermistor, how you can fabricate them. Okay, then we have also seen a semiconductor PN junction sensor like a diode or a BJT working in different modes can exhibit different thermal dependence characteristic. Typically for a silicon junction operating at say 10 milliamp, the slope, which is basically the sensitivity, was found to be approximately 2.3 millivolt per degree Celsius, and it drops to about 2 millivolt per degree Celsius for a 1 milliamp current, and we utilize this principle for measurement of temperature very accurately. Okay, then thermistors we have seen in detail. We have seen different sizes and shapes of thermistors that are available in the market. Then thermocouple was another temperature sensor that we have seen in detail, and we have seen that they are based on Seebeck effect. We have also considered other effect, Peltier and other things, through which we have understood this thermocouples, and we have found that these kind of thermocouple do not need any kind of external biasing. Simple or temperature difference at a hot junction and cold junction is more than sufficient to give you an idea of the heat flow, or EMF is generated, and based on that you can calculate other values. We have done a detailed calculation of this AB, where I have this Seebeck coefficient of material A and B, and for a material pair also we have calculated these Seebeck values. Okay, we have seen their advantages and disadvantages. We have seen that the thermocouples have wide temperature range and have fast response time as compared to what devices we have seen. They are simple and rugged construction. They are low cost devices because it is simply two different metal wires connected together. But of course, we have seen that there are only few combinations of these metal wires that industry follow. Okay, mostly they were based on platinum. Okay, and they were suitable for harsh environments. Okay, the application of these thermocouples were enormous. We have seen that it can be used in furnaces and boilers, gas turbines, heat treatment plants, and etc. Okay. Then piezoelectric transducer, we have seen in detail that how these devices can convert a mechanical energy, including all kind of mechanical inputs like forces, pressure, acceleration, vibration, into certain form of electrical energy. Okay, based on a piezoelectric effect. Okay, we have also derived a piezoelectric transducer equivalent circuit, and we have seen that it is kind of charge generation device, capacitor and resistor in parallel, and the output was taken across this leakage resistance RP. Okay, then we have compared it with a strain gauge, and we have found that in some point of view piezoelectric transducers have excellent properties, particularly the dynamic response of piezoelectric devices were very good, but they were not suitable for static measurements, because in the static measurement the charge that it generates cannot be stored, it vanishes easily. So it has a major advantage in terms of dynamic responses. Okay, and for static measurement these strain gauges were found to be more suitable. Once we have discussed these meters and the transducers, we have also discussed about the different signal conditioning circuits. Okay, in the signal conditioning we started our discussion with the operational amplifier, and then we talked about the instrumentation amplifier, and we also discussed about filters. Okay, in the op-amp we have seen in detail their important properties. Particularly we have found that these op-amps has high gain, they can be used as differential amplifier, they have high input impedance and low output impedance. I mean, the ideal characteristics we have seen. And then we went to instrumentation amplifier, and we have seen that 3 op-amps can be configured in 2 stages to make a very high input impedance device. Okay, so this was kind of constructed using op-amp, and the gain of this instrumentation amplifier was found to be like 1 plus 2 R1 by R gain into R3 by R2, and this resistance was something was very interesting for us, and we found that using this external resistance the gain of this instrumentation amplifier can be tuned. Okay, we have also discussed filters. We discussed that a filter selectively passes signals within a defined frequency band while attenuating components outside this particular band. Okay, so this helps us in suppressing noises, interferences and any undesired spectral components. Okay, and we have seen two different type of filters, active and passive filters. The passive filters were only using resistances, capacitances, inductances, while active filters were also utilized op amps. Okay, so they can, along with filtering, they can also provide you certain gain, while the passive filters were not capable of. Okay, we have seen four different kind of filters: a low pass filter, high pass filters, band pass and band reject, or we called it notch filter as well. Okay, and you can see their characteristic. We have discussed all these characteristics in detail. In the week 10 of this course, we continued our discussion on signal conditioning, and we have seen AD and DA converters, including their constructions and shielding and grounding, which we found to be very interesting, and it was essential part of this course. Okay. So we have seen that modern measurement systems use digital processing units such as microcontrollers, and that's why you require analog to digital converters and digital to analog converters. The DAC, digital to analog converters, we have found that there are three different kind of DACs which are very important. One is the register string type DACs, n-bit binary weighted registers, and R2R ladder kind of DAC, and we have seen their operations. ADC was found to be little complicated, and the conversion from analog to digital occurs in three different stages: sampling, quantization and encoding. Okay, and we have seen that what is the role of a sample and hold circuit. Okay, and we discussed a different methodology to convert analog signal to digital signal. Particularly, we have seen the potentiometric AD converter. We called this was based on successive approximation. We have seen voltage to time conversion method. This was again using a ramp generator. Okay, we have seen voltage to frequency conversion method, which we also call a integration type, and then we have seen a dual slope integration method, which all of them having their own advantages and their own disadvantages. Okay, then grounding and shielding was another concept that we got introduced in this week 10. Here we discussed about the utilization of grounding and shielding, and we found that they are very useful in reducing noise, interferences and measurement errors. Okay, we have seen different type of grounding like earth ground, chassis ground, signal ground, and why to measure earth electrode, why measuring earth electrode resistance is important. And then we found that there are different techniques for measurement of earth resistance, like fall of potential method, then dead earth method, clamp on method and 4-point method, out of which fall of potential method or the 3-point method we have also discussed in detail. Okay, then shielding was another concept. So modern instrument systems process very small signals in the range of microvolt to millivolt, and these signals can easily be affected by EMI and EMC. So electromagnetic interference, radio frequency interference, power line noises, crosstalk from nearby circuits, these are some of the important signals from which you want to shield your device. Okay, and this shielding can provide or prevent your device from all these interferences. Okay, three type of shielding is required that we have seen: electrostatic, magnetic and electromagnetic shielding. Okay, we also saw shielding of cables, because this can be one of the major source of interferences. So we have seen that cable with foil shield and braided shield can be used, a coaxial cable can be used, and how interferences or how shielding is provided in this coaxial cables and so on. Okay. In week 11, we started our discussion on data acquisition system. We first got introduced to data acquisition system, and a sensor or transducer was first part of this data acquisition system that we have discussed in our previous modules. Okay, we have seen analog data acquisition system and digital data acquisition system. We also studied about oscilloscopes and signal generators and analyzers. Okay, so in oscilloscope we have seen them in detail, but a typical oscilloscope consists of particularly the analog oscilloscope had all these parts: a probe, okay, vertical amplifier, delay line, trigger circuit, time based generator, horizontal amplifier and a CRT. So cathode ray tube also we have seen in detail, and display also we have seen in detail in our next module. Okay, the oscilloscope we have seen its working in detail. They works by deflect an electron beam based on an input signal and time based signal. Okay, input signal enters through this probe, signal is amplified by this vertical amplifier, this signal passes through this delay line. Okay, this trigger circuit synchronizes the signal, time-based generator produces sawtooth waveform, and sawtooth signal drives the horizontal amplifier, and vertical signal control vertical deflection, while horizontal signal controls the horizontal sweep. Okay, and this is how the signal can be generated. Maybe we have seen that there are two modes, normal mode and XY mode. In the XT mode, which was the normal mode, we have seen that voltage can be swept with x-axis as time, while in the XY mode we have seen that we can sweep a voltage with another voltage. So say this is input voltage, or say this is V1, this is V2. So these two voltages can also be swept with reference to each other. Okay. In 12th week, we discussed different analyzers, like we have talked about wave analyzers. We also got introduced to the harmonic distortion and their distortion analyzers. Then spectrum and logic analyzers was something that we have seen. We also got introduced to process control, and we talked like this process control is a part of another big course, which is a control system. But then also we got introduced to this process control, and in the process control we have seen a totally digital controller, which was programmable logic controller, PLC. We have seen that in detail, and we also talked about different display devices. Okay. Signal analyzers, we have seen they were the device used to examine signal in frequency domain to understand their frequency component, because till now whatever we have seen was in time domain. Okay. However, if you want to analyze distortion, noise and spectral, complete spectra, you may also need to see it in frequency domain, and this signal analyzers helped us with that. Okay. We have seen different type of signal analyzers like wave analyzer, distortion analyzer, spectrum analyzer. Okay. We have seen that a spectrum analyzer sweeps the signal frequency band and display a plot of amplitude versus frequency with an operating range of 0.02 hertz to 250 gigahertz, while a wave analyzer measures the amplitude of a single frequency component within 10 hertz to 40 megahertz, and accordingly the equipment was also made. We have seen their constructions also. Okay. Distortion analyzers measure energy present outside a specified frequency band and indicate the harmonics. Okay. Then we also talked about harmonic distortion analyzer, and we have seen that 4 different type of harmonic distortion analyzers are there. Like we have a tuned harmonic distortion analyzer, heterodyne type of harmonic distortion analyzer. We have also a digital harmonic distortion analyzer, but the fundamental suppression method is something which is very popular, and we have used a notch filter to separate out a fundamental frequency component from the harmonic, and then harmonic was transmitted. We have seen that it can be also operated in manual as well as in the automatic way also. Okay. In the process control, we have seen that how feedback control loop helps in improving the performance of the system, and in that feedback control loop, controllers played very important role, and we have seen different type of controllers like on-off controller, a proportional P controller. We also have seen proportional integral or PI controller, PD controller, PID controller, and in all together we have also seen totally different digital controller, that is a programmable logic controller. Okay. Then we also saw display devices and recorders, the output devices on which the signals that we have generated are displayed. Okay. So the output devices can be classified into different type based on the nature and use of the output. We have seen that we have single number output devices, we have time domain output devices, and we have machine interpretable output devices, and we have seen different digital component of all of them. Okay. So after completing this course on measurement and instrumentation, we are now able to explain working principle of measuring instruments. Now we are able to suggest how to calibrate and interpret analog and digital meters. We are also able to choose suitable transducer for particular given application, particularly by knowing the input, output and its transfer characteristic. We are now able to analyze and process signals using amplifiers and filters. We now know how to use shielding and grounding concept and design simple data acquisition system. These are some of the text and reference books that you can still refer for your further studies. I am really thankful to my TAs Moti, Anita and Tushar for helping throughout this course. Without their help, it was not possible to cover this vast topics. I have taken their opinion on time to time, and that has helped me really to tune this course according to the current need. Okay. I also like to acknowledge students of our department at IIT Guwahati who has taken this course in past and still pursuing this course. They have given a lot of feedback in the class. I learn a lot of things from them in the class, and that has helped in shaping this course. Okay. My colleagues from the department and other departments and centers with whom actually I have directly or indirectly connected for this course, for their feedbacks on the slides that I have shared across this course. Okay. I am really thankful to the authors of the textbooks, reference books and research papers whose content I have taken to teach this course. I am thankful to the CET, coordinator of the CET and entire team of CET who has directly helped me by giving different slots to record these sessions. I hope that this was helpful for many of you who are watching. I am also thankful to the NPTEL platform, NPTEL team from IIT Madras and IIT Guwahati for giving me this opportunity to float this course, to run this course smoothly, and giving me all the facility that is required to run and record this course in the time frame. I am really thankful to everyone who has contributed to this measurement and instrumentation course. Okay. So, what you measure today shapes what you innovate tomorrow. With this positive line, I will end up this course. Thank you.